I'm so excited to start calculus. This is fucking exciting.
You should be. We're talking about the derivative.
I'm not.
A little bit. Just a little bit. You're not really going to get to what the derivative actually is yet. The derivative comes out of the difference between average and instantaneous rate. Average and instantaneous rate. Now, average rate, or average rate of change, you guys have been talking about since pre-algebra. Does anyone know what the math name for average rate of change is?
Slope.
Slope. Slope. So, M, your slope, is also your average rate. Instantaneous rate, what's that mean? Nope.
At a single
At a
time.
single point.
At a single point, yes. Instantaneous rate is what happens at a single point. The average rate is what happens, you know, if I'm just like, if I drive to school today and I drive 1,000 feet in 10 seconds, I've averaged 100 feet per second. If along the way I speed up and hit a tree,
Oh.
that might not change my average, but I might not be interested in my average. I might be really interested in how fast I was going right at the second when I hit the tree. That's probably much more interesting to me than my average of my whole journey from home to the tree. Similarly, instantaneous. I left out a whole syllable here, didn't I?
I think I added too many syllables.
We can then what the average to the correct spelling.
Yeah, I was gonna say, but I didn't
Thank
want
you.
to.
All right, average and instantaneous rate. Okay, average and instantaneous rate. I have a graph up here. It is the graph of height versus time of an object that falls under Earth's gravity, not in metric units, in English units. For the physics kids. Physics kids may have an advantage with this one.
Great.
Okay, even if an object falls straight down from a height of 288 feet, if you graph its height over time, it appears to be a parabolic curve. Those of you not in physics missed this discussion earlier in the year. Yes, the object travels in a straight line, but as time passes, you can use a parabola to describe its changes in altitude. Okay? So the following object is just doing this, but how high it is at various times will graph a parabola.
Are you throwing it or are you dropping it?
Dropping it.
Oh, God.
So, yeah, the object is just going straight down. The object's path, well, I have it set backwards here, but let me fix that. The object's path looks like this. There's the falling object. Boom. And it bounced back up a little before I hit pause. Even though its actual motion is down here in a straight line, its acceleration can be graphed like that. Okay? So this is just some falling object. When it hits the ground, there's a couple things we can talk about. We can talk about the average speed it took. But falling objects, physics kids, do falling objects fall at a constant speed?
No.
No, they accelerate. Okay? So the average speed won't match the actual speed at which it hits the pavement, and that's what we're more interested in. Now, physics kids, you had a velocity equation for that, but we're going to pretend that equation doesn't exist. We're actually going to show how that equation relates to the derivative next week. But for now, how would I find the average speed of a falling object from here to when it hits the ground?
Slope.
Slope, exactly. So let's talk about that slope here.
And do you draw a line?
I would indeed.
Oh.
Somewhere around
4.25 possibly.
Oh, you dragging? Oh, dang.
Yeah, but I've only got it set to
Increase it by 0.05, see
It's
what
like
happens.
delta, whatever.
yeah, exactly.
Yeah.
So I can change it by 0.01. That should let me.
Ooh. Close.
All right, so it's between 4.24 and 4.25.
4.25.
It's a little closer to 4.24 because I have slightly higher. So that's going to be as close as we're going to get towards 0 now. All right, that'll make the math a little bit more annoying. But oh, notice up here. Okay, so average speed is the. What's really fun is if I switch it back to a writing tool first. Average speed is the slope of what's called a secant line.
Ooh.
Latin kids, anyone know what secant means?
Sever.
Sever, to cut across. Well, it does mean whatever cosine, but that's not the Latin meaning. The original Latin meaning of the word is to sever, or to cut, or to sort of take a shortcut. That's the average speed is going to be the slope of that secant line. And incidentally, look at what I set up here. I told Desmos to calculate. This is basically, this dot is controlled by the slider with the letter B. This dot is controlled by the slider with the letter A. Look at what I have up here.
It does
F
this?
of B minus F of A divided by B minus A.
What?
It's calculating the slope.
That's cool.
Yeah. So it'll just, I just put that equation in there, it's giving me the answer. So the average speed of this falling object, the average speed beginning at 0 and ending at something, okay, that average speed is the slope of the secant line. That equals negative 67.84. And the way I've set this up, this will be feet per second. That's still pretty fast, covering twice the length of this classroom in 1/1000. You wouldn't want to hit a ground at that speed.
How heavy is this thing? Or does that matter?
Does not affect the speed of a falling
Oh,
object.
that's right.
Unless it gets to a mass that's a significant percentage of the Earth. Gravity is really an attraction between two bodies, but when one of those bodies is the planet Earth and the other one is you,
Right.
it's a tug of war that you've just lost. So that's why we say all objects fall with the same speed regardless of mass, unless we're talking about another planet, and then it's a whole other equation. What did we say in physics last period? These formulas are true until they're, as long as they're true, and then they stop being true. Yes,
Someone told me last year that calculus is just the distance under a curve. Is that true?
it's part of it, but not the part we're going to get to today.
Looks like we're measuring a distance under a curve. Then.
No, we're measuring a length that happens to be under a curve in this case. It would be above a curve if this were exponential growth. If this were a curve that like smiled instead of frowned, we'd be below it, not above it. But a good connection there. All right, so this is your average speed. Is this the speed at which this guy hits the ground?
No.
No. How can we find that? We're sort of guessing at it.
What does this show then?
This shows, this is this x and y, this y value minus this y value, divided by this x value minus this x value. That's a slope, right? What it means in this graph is it's his average speed. He started at 0 feet per second. He hit the ground at a speed we don't know yet. Physics kids have a formula for that, but I'm asking them not to use it. And his average speed along the way was the slope of that secant line, which is your y2 minus y1 over x2 minus x1. All right, so what's the difference between average and instantaneous?
One is a point.
One is a point.
Average.
Average is over the whole thing.
What happens?
That you care about.
Actually, it's over the whole domain that you care about. It's actually not a bad way to put it. Let me
And then
Save this real
instantaneous
quick.
is exact at that second, right?
exact at that second. Is it at a second?
Whatever.
Is it at a millisecond?
Whatever unit you care about.
Planck second.
Now you're moving into when you say whatever you care about, you're moving into like sig figs a little bit. But what does an instant really mean in math?
Planck.
No,
Yes, sir.
Planck is not a limit in math.
Intersection?
No, instantaneous means as small as you can possibly imagine.
Singular.
It's like a limit.
Negative infinity.
Now remember, negative infinity is not small. It's huge in the other direction.
So it's infinitesimal.
0.
Infinitesimal is a good word. It's as close to 0 as you can imagine. Here's the problem with this. That's your average rate. It's just the slope. That's some, you've been doing average rate with different words since 7th grade, most of you.
It's
Hang on a second.
paradox.
No, but that's not a bad way to start thinking about it. Okay, if we're really interested in, and if you're falling off a building, you probably are really interested in, the instantaneous rate, which I misspelled again. Maybe this video will just go direct to the students and not through YouTube. Instantaneous rate. Okay, here's the problem you get. Okay, we'll stop critiquing the handwriting now. We can critique the math, but okay. Instantaneous rate, here's the problem with figuring it out. If you take y2 minus y sub 1 over x2 minus x sub 1, and you're only talking about a single point. What's the problem with that? Well, it starts looking like y2 minus y sub 2 over x2 minus x sub 2. It looks like 0 over 0, and remember when we discussed limits, I didn't put this on the last test, I said this is never possible. Talked about this with rational expressions too. This can never happen. It's called an indeterminate form, and if you get this as an answer, there is always something else you must be able to do. Natalie, you have a question?
How does it start looking like y2 minus y2?
Okay, this is your slope formula, right?
Mm-hmm.
And slope is average rate of change.
Yeah.
Slope of a line, it has to be a line. So that's why the average rate of change is often called a secant line. It takes a shortcut.
Right.
It cuts across the curve somewhere. Okay? If we start talking about the instantaneous rate, what is happening at just this point? You can't use a slope formula. Because if you're at a single point, you would be trying to find what is, let's see, when you hit the ground, you're talking about the same point. You're talking about the same y value and the same x value in both places. Does that make sense, Alan?
Yes, it does.
Okay, so you're going to get 0 over 0, and that's never an answer. An indeterminate form is never an answer, so there must be something else. So I'm going to give you guys a way to guess.
Why is it called instantaneous rate if it's only not going over something, over time or something? It's just right
That's
there?
actually a great question. I'm not sure what the answer to that is. Why would we call it a rate at all if
Right.
nothing is happening? But if you take a photo of
Why
a
wouldn't
car...
you call it an instantaneous moment or something?
Well, let's think about this for a moment. If you take a stop. If you take a photo of a car right when it hits a tree, is there any motion in that photograph you're holding?
No.
No. But was there motion as the car hit the tree?
Yes.
Yes, but it sounds contradictory, right? We're kind of flipping back and forth between talking about the photograph and the impact, which are two different things.
And the impact in real life.
Yeah.
Okay.
Calculus is a way to get around that sort of paradox. All right, we're going to start by guessing. All right, we don't really guess when we get into the math, but we're going to start by guessing. Okay, and here's what I'm going to do. The flaw in using this to find out how fast I hit the ground is that it covers too wide a domain. Like, how much of this domain do we actually care about? Brandon alluded to this a minute ago.
Only up till nothing.
But, I mean, we care about the domain until right here at about 4.24 seconds
Oh.
when it actually hits, right? Okay, so I'm going to start shrinking this domain. What's halfway between 0 and 4.24?
2.12.
2.12. Okay. Luckily, I've set this up so that I can move, I can restrict, and play around with the domain.
You can go halfway.
Yeah, I'll try going halfway. Why not?
Like in between
So,
the two.
because they're moving halfway, so at first we were going from your house to the tree.
Well, now we're going from the top of the building to the ground. I'm mixing my metaphors.
Oh, so now we're halfway down the building?
Yeah, now we're well, in terms of time, we're halfway down the building, but when you accelerate, the distance is different.
God, I don't like this.
you missed physics. Some of half the class took physics, you guys didn't. But yeah, because you're accelerating, when the time is halfway done, you're less than halfway to the ground.
This is time.
Yeah?
This is half. This is how far I am from the ground.
Not automatically. Half the time, because if you constantly speed up, if you keep speeding up and speeding up and speeding up,
You're covering ground faster?
yeah, you keep covering ground faster each second, then when you're halfway there by time, you're less than halfway there by distance.
I got
Because
you.
each second
That was-
after
okay,
that's
that was
more.
good. I got
Okay, all right. So, but still, we have a new average rate of change now. At this point, between these 2 points, I'm going to on your fall, you will have an average speed of negative 114.24 feet per second. Okay, and now we're going to move in closer. Zach, go ahead and jump to, hang on a second, let me save it first. Let me save this plate, slide, whatever
So
you
are we
wanna call it.
shortening the distance or are we shortening the time?
We're shortening the time because that's our x variable. We always do this in a way that shortens the x variable, the independent variable. Okay, and now,
Wait, I have a question.
yeah,
Wouldn't the instantaneous rate when we hit the ground be 0? When we're done, we hit it, It's over.
Physics kids, do you usually hit the ground with kinetic energy?
Yes.
Kinetic energy is 1/2 mv squared, right?
Yes.
If your velocity, your rate was 0, how much kinetic energy would you have when you hit the ground? I would go ahead and jump off a 3-story building and not worry.
Woo!
I don't recommend that. You obviously have a velocity, or else
Something's gonna happen.
something's happened. Take Zach, take us to just type.
Alright.
Go back 2 spaces and type. Take us. Whoa, not there.
Oh, hey.
Slow down, cowboy. Take A to right there. Back to type in 4.
Could you just type in
No,
instead of
4
very
seconds
close
total.
to-
No, type in 4.
A
Just
equals 4.
A equals 4, not 24. 4.
There we go.
There we go. Okay, now, all right. Can you guys even see the difference between the segment and the curve here?
Barely.
No.
I'd have to zoom in to see it.
So wait, so are we measuring the slope still or the instantaneous rate?
We're measuring the slope still. We don't know how to find an instantaneous rate. We have no idea what that even means, really, as you're demonstrating with some wonderful questions.
So are you
Yeah.
trying
Hang
to
on.
are you trying to get rid of the distinction between like acceleration and velocity?
Not in the least, but that's a fascinating question. Actually, you and I should unpack that later. Okay, so now at t equals 4, according to my little slope generator up here, our instantaneous rate
Oh, we said we
Is-
weren't finding it.
our average rate of change, thank you, is negative 131.84.
Okay.
All right, we're getting a
Why
little
is
closer.
it negative?
Which way are we going? In terms of height?
Down, but time is increasing.
And height is decreasing, and if you have a negative divided by a positive, the result is negative.
Okay.
Also notice this slope is tilting down.
Right.
Go back to algebra 1 for a minute there.
Down.
If it's heading down from left to right, it's a negative slope.
Okay.
Remembering your algebra 1 while tying this in is honestly a challenge.
It is. I'm feeling it.
Right. Okay, let me save this one. I want to build suspense when people look at this in the Google Drive later.
Awesome.
What's gonna happen next?
The recording is going to cut off.
I hope not. Somebody check. Okay.
I'm looking at it every once in a while.
Excellent. Thank you. All right.
That's what I get paid to do.
That's why they pay you the no bucks at all. Okay. Change 4 to 4.2 for the A. Change it to a mouse first. Thank you. Okay. Now look at those 2 points. They're practically on top of each other.
Wait, so if it never hits 0 when it hits the ground, how do you know you've hit the point of instantaneous?
In real life, because you feel the impact.
But no, in math, because
Do
the number keeps increasing.
We're actually not going to answer that today. Oh, no, yes, we are going to answer that today. You're going to guess at that today.
Wait, how do you? Okay, I guess I'll just keep waiting over here.
The super short answer is right now you don't. Okay, so at
Don't know,
4.2,
just keep plummeting through.
we're at negative.
through
Well,
the earth.
this is getting a little Zeno's paradox, isn't it? I mean, the whole point to Zeno's paradox was he said to Pythagoras, your math is insane because an arrow can never hit a target. It keeps getting closer and closer and closer, and according to you, you can keep dividing forever. So how can anything ever impact anything?
Okay, why did you have to say this?
Why did Zeno have to say this?
Mine.
Yeah, this is a little mind blowing here.
Yeah, it is.
I have a question.
That's the point. Well, part of it was actually, honestly, I mean, math, science, philosophy, they were all overlapping things, and they overlapped with like religion and cult behavior back then. Pythagoras was a cult leader, and Zeno's ideas were dangerous, his ability to, get recruits and maintain control.
That's why you killed him.
There's a legend that Pythagoras killed a man for talking about the square root of 2. Talk about that later. Yes?
How do you find the slope?
How do you find the slope?
How do you keep finding it?
I have this slope generating thing up here. See how I have f of b minus f of a, like f of x minus f of x over b minus a? I've set this up so that's a y minus a y over an x minus an x
So we'll get,
between these 2 points.
we'll get to do an example problem.
You'll have to find a slope. We'll talk afterwards. But yes, you are going to have to remember how to pull out your calculator and find a slope. I haven't planned on reviewing that.
What would a problem? No, see, what would a problem look like?
I'll get to that at the end. Okay, so we're getting closer now. Zach seems to hit around 4.24. We'll use that as our thing. So take it to t equals 4. After I save this, take it to t equals 4.23. We're getting closer and closer and closer.
But we know it doesn't hit exactly at 4.24, right?
No, but I'm definitely being a little lazy with the sig figs here,
Okay.
because that threw me off when I had to change the coefficient for gravity. Pardon?
Because you can't see it.
Should I just zoom in? Okay, let me, I'm gonna zoom in, let me,
Actually, you kind of can.
kinda can, but we can do that. We have that power.
Zoom.
Let's have the power to keep writing on it by mistake.
Zoom, zoom.
You wrote
Whoops.
Whoa. Josie.
It's a pretty lame
Zach, you
superpower.
wrote 4.3.
Alright, 2, 3,
Yeah, we want
Yeah, I
4.
tried.
You tried.
I tried.
That's all right.
Keys are hard.
Okay, now, yeah, that's, wow, look at that. It's really hard to see.
Oh, wow.
Ours will line just end eventually.
I set it up to be a segment.
Uh,
It's still really hard to see the difference between the line and the curve. There is one. You can never perfectly.
curve?
I think the computer just doesn't do it with your delta.
I
It's
guess
like
we found out where
It's
it
screen
was.
resolution, essentially.
screen resolution.
Yeah, but yeah, you can never in real life, in the abstract, you can never superimpose a line over a parabola, but this thing's screen resolution can't tell the difference. All right, so what does my slope generator say?
Negative 135.52.
Negative 135.52. That's at 4.23. Okay, so
We found out where it hits the ground now.
we're getting
More or
there.
less.
So, okay, so now at t equals 4.23, your slope is negative 135.52. What was it a minute ago?
Something.
Negative
Something different.
135 something.
Negative 135 something. Okay.
0.04.
So we're getting 0.04. All right, so we're getting a little bit there. Let's,
And this
Why is
line
it gaining
2%.
slower now?
it went from negative 1, hold on. You
Gosh.
just mistook velocity for acceleration.
Uh-oh.
God.
So
Um,
confused.
No, it's, think about this, Natalie, for a second,
Okay.
okay? I give you $1. I give you 50 cents.
Um,
I give you a quarter.
yes.
I give you a nickel.
Mhm.
I give you a penny.
Yes.
Am I slowing down? Or is the amount of money in your bank account increasing or decreasing?
Increasing.
But is it increasing at a slower rate?
Yes.
Okay, I am decreasing the acceleration,
Of
but you are
money.
still accumulating positive stuff. You're still gaining more money. If you go from negative 135.04 feet per second to negative 135.52 feet per second,
Uh-huh.
that's like giving you the
We're
penny.
increasing slower.
Yeah,
Okay.
that's the difference between like the velocity is still increasing. You're still hitting the ground a little faster,
Uh huh.
but you're not.
Now.
Because we're shrinking the domain so small, there's less of a change in the range.
Okay.
So if I only jump a tiny bit on the x-axis, I'm only going to jump a tiny corresponding bit on the y-axis. And that's going to get more pronounced in a second because now,
You just saved that, I think.
I saved it in the wrong place, I think.
Oh.
So faster is, because now what we're going to do is all I want Zach to do now is type a 9.
Boom.
Okay, and now look at our slope. T equals 4.239, and our average rate of change is negative 1.35.664.
Were we trying to get it to hit the other point? Or at the bottom?
Yeah, that's a good way. We're trying to get as close to the other point. We're trying to get as close to the other point as we can without running into the 0 over 0 problem. Because if they were the same point, the slope between them is 0 divided by 0, which is impossible. So we're
How
trying
do
to
we
guess
ever
at what's
find
going
the
on.
instantaneous rate?
Okay, hang on.
4.2.
Okay, Zach, type another 9, Zach. Okay, so now we're at T equals 4.2399, and my slope is negative 135.6784.
Should I zoom in?
Not yet. I don't mind them looking right like this right now.
Okay.
Yes.
So, if we're never going to overlap the points, because that'll give us 0 over 0.
Yeah.
How in the world do we find an instantaneous thing if they do not ever collide?
Is Zeno's paradox right? Can I never touch this wall?
No, you can touch the wall, but the point can't touch the point.
Yeah. The point can't touch the point without blowing up our model. That's another physics conversation we had.
Blowing up the model.
The model is that you can find changes in speed with slope. That fails when you go from 2 points to 1 point. We need another model. But for now, we're just guessing and today is all about figuring out the question. The answer happens next week.
Great.
Figure out the question.
The question is, how fast are you going when you hit the ground in this case? And look at what's happening here. It's been 135 point something for 3 times in a row. And in a moment, hang on a sec, Alexi.
Hang on.
Type in other 9, Zach. Wait for it, right there. Okay, so now, what we're looking at is t equals 4.23999, and it looks like my slope, which is my average rate of change between these 2 points, there's still 2 points, 0.67984.
Why do you keep making the
So
same
you're telling me that unless I destroy these 2 points, I am never going to, they are never going to touch.
Well,
Hey guys, wait, hang on a second. To what, Alexi, to what value in feet per second do you think this slope is headed towards?
What is the question?
So what, we seem to be closing in on something. Like you said, we're moving less and less each time as we shrink the domain.
Right.
Negative 135.52, negative 135.66.
Are we getting
negative
closer to a 0%
135.6
change?
Well, hang on, negative 137.678, negative 135.67984. I'm gonna have Zach put in one more 9.
Let's see it.
Go ahead, Zach.
Boom.
Boom. Okay, look at this. Negative 135.67998.
Wait, what's this thing?
When you start getting a bunch of 9s after a point, what's usually
That equals like 1.
it brings the next week. Just if you're getting 9s after the 7, I would assume we're heading towards, and this is a guess, that we're heading towards an 8 in that place, in the 100th place, because the 9s are starting to stack up with the 1000th place. So,
I have a quick question.
one sec.
Yeah.
Conclusion first. Mr. B's guess is that the instantaneous rate, one of these days, I will spell it right on the first try, is that the instantaneous rate,
Forgetting the X.
probably, equals negative 135.68 feet per second. That's how fast I think you'll hit the ground, or rather that's how fast I think you'll be going
Why are we doing another 9?
0.4 feet above the ground, because we didn't get that close to 0. That's my guess, because it looks like, again, I'm starting to accumulate 9s back here, which just makes me think that it's heading towards this as an 8.
That seems like a really inefficient way to find the instantaneous speed.
There are more efficient ways if you have a good model. We seem to be headed towards something. When you're heading toward, how do we deal with heading towards something, but when we weren't able to deal with getting there? What do we call them?
Limit, right?
Limits.
Yeah.
A limit, it's where you're headed and you don't have to care whether you actually get there or not.
Wait.
So next week we're going to talk about how to use limits to find what is called,
But wouldn't we care where we hit the ground or how fast we hit the ground?
oh we do, but mathematically the way to get around, like you were saying, once the 2 points are the same, you get 0 over 0, right?
Right.
So we can't actually get there.
So Pythagoras.
But we're going to use limits next week.
Are we going to use limits to try and create the 0?
We're going to use limits to get rid of the 0 over 0.
Wait, so
To
like.
get rid of it?
Yeah, next week's we will use,
God, my brain.
hang on a second,
Same bad time, same bad channel.
we will use limits to find the derivative.
Is there work we can do behind this?
I'm going to give you some problems where you're going to try and find instantaneous rates of change using charts, plugging in closer and closer
Like Desmos?
x values to a y. If you want to type it into Desmos, sure, but it might be faster with a calculator to just trace. Okay, Brandon, quick question.
Why don't we just graph y equals 0 and find out when they intersect?
Because y equals 0 is the x-axis. And that will give us a time and a position. That won't give us a slope.
Yeah, but then we can use that point and plug it in to get our slope.
No, we can't, because we still just have one
It'll be
point.
0.
That point will be the instant when we hit. We'll
It'll
still
be the
stuck.
same point you're looking at.
Yeah, you'll still be trying to find the point from one point to. I'm sorry. You'll still be trying to find the slope between one point and itself.
Oh, okay.
You're still going to get 0 over 0,
Oh,
which is never, ever, ever the actual answer. Never. But sometimes we have to use limits to work around that. And we'll start talking about
I
that.
meant like that would be the time it takes to get.
No,
to the
won't help.
ground.
Well, we already know the time it'll take to hit the ground.
Okay.
You already found that. Yeah, physics equations for that.
Yeah.
The derivative is a name for the instantaneous rate of change. It is also the name for a tangent line to a curve. Secant lines cut across curves. Tangent lines touch.
You just said the tangent is the instantaneous rate?
Tangent, derivative, instantaneous rate, they're all overlapping words we're going to use next week.
Okay.
This is going to drive Natalie nuts because it can't be done in one day. But that's okay.
And it's a
I'll show you guys
Think
one
about
other
it.
thing real
And
quick.
it's a Friday, so
And it's a Friday.
I'm gonna go home like, Mom, calculus.